Hiya. Okay, so next up in our list is 1.3.2, which is orthogonal matrices. And basically we're going to look at matrices coming from orthonormal bases. So here we're going to assume that B is an orthonormal basis of En. So remember last time we said that En is going to be an n-dimensional Euclidean vector space with an orthonormal basis. And we're going to ask ourselves, what's the condition on the transition matrix that an ordered set of vectors C also forms an orthonormal basis? So what we're basically asking is, if I have B orthonormal, and I want to go to C, right? So remember here, normally we'll use a transition matrix. We're asking when is C also orthonormal? And the answer to this question is actually not too bad. It's basically when the transition matrix is orthogonal. So this transition matrix here is going to be exactly what's going to define it. So it's when the transition matrix is orthogonal. So orthogonal, I don't know if you've all seen this before, but just in case not, an orthogonal matrix is basically an n by n matrix if its product with this transpose is equal to the n by n identity matrix. So what's this? So it's some matrix M, right? It's the product with this transpose. So the transpose times itself is equal to the identity matrix. And that's all it is. So here, if you recall, this is 1, 1, 1 with 0 everywhere else. Okay, so that's what orthogonal matrices are. We haven't shown that this transition matrix has to be orthogonal, so we'll see this in a minute. But first, what we're going to do is we're going to quickly look at this matrix here, this orthogonal matrix, and we're going to look at its determinant. Because one thing to kind of note is that orthogonal matrices have a nice determinant, and that's that the determinant of an orthogonal matrix is always a plus or minus 1. So orthogonal implies that the determinant is plus or minus 1. And this is not too hard to see, right? Because we end up having that. So we start off with 1, right? 1 is equal to the determinant of the identity. From above, so by above, we know this is equal to the determinant of M transpose M, right? This is by definition. For people who've worked with determinants, we know that we can split the determinant in two. So this, we can take the two multiplications and come out. And the determinant of a transpose is equal to the determinant of itself. And so we get determinant of M squared is equal to 1. And so the determinant of M has to be equal either plus or minus 1. So in particular, we know that it's always non-zero. And so it's a transition matrix from one to another. So that at least we're happy about. But we need to show that it's actually an orthogonal matrix. So what we're going to do is we're actually going to show the following proposition. And here we're going to start off with some orthonormal basis. So B here is orthonormal for an n-dimensional Euclidean vector space. And we're going to look at, and we're basically trying to show. So here I'll write this underneath. So we want to show that C, sorry, we'll do it with this one. C is orthonormal if and only if the transition matrix BTC is an orthogonal matrix. So that's the kind of key points, that we have C is orthonormal if the transition matrix, if and only if the transition matrix is orthogonal. So let's kind of see this. Here I'll write it above. C orthonormal if and only if BTC orthogonal. So that's basically what this proof here is trying to show. So let's look at this. What we're going to do is let's look at the ijth entry of BTC. And basically we're going to just denote it as aij. So here we have this aij. And so this is the kind of notation we're going to be using for this transition matrix. And so here we want to look at this transition matrix. Remember how it takes us from one inner product to another. So we're going to look at the inner product of fi and fj. Okay, so here we look at the inner product, and we want to show their orthogonal or their orthonormal. In other words, we get the Kronecker delta. So here we have this. What we do is, this is kind of something we've already seen quite a few times, so this is why it's not hidden in the notes. Basically, we take each one of these and we look at it in the EI vectors, right? So these are the coming from EI is in our original basis. Then we use linearity, right? So we're able to split all the things out. So this notation, by the way, if you're not used to this notation, KL equals 1 to N. This notation is the same thing as what we had earlier, where we had K is equal to 1 to N, L is equal to 1 to N. So it's basically just a shorthand notation for kind of merging them together. That's all this is, by the way, notation. Okay, so we have this equality. Here, this we know is the Kronecker delta, right? So we can kind of just convert it in. And then as before, we know that this is just going to give us a dot product, right? So this gives us the dot product. So this we had already seen before, right? None of this should be new. This we saw, I think it was in 1.9, right? So all of this part is 1.9. This whole thing is 1.9 from before. Now here, one thing we're going to note is because, like here, we can take the transpose of this, which would just change the indices. So this is where we get the IK. Transpose changes indices. Transpose changes in swaps is a better word. Swaps indices. And this summation is nothing more than the matrix, the transition matrix transpose, times the transition matrix itself and the ijth entry. So basically what we have is to show, what we want to show is, so what we have is C forms an orthonormal basis if and only if this is equal to the Kronecker delta. So if and only if we have this, right? If this is kind of true. In other words, since we showed that this whole thing, right, is equal to this is true if and only if this final part here, this BTC T BTC is equal to the Kronecker delta, right? So this is what this part is showing, right? So this is from above. Now, when is this true? Like, what is this equivalent to, right? So what we're trying to get to the fact that the matrix is orthogonal. Okay, so this is equivalent to actually exactly what we want. It's equivalent to this transition matrix equal to the identity. Now, why is this true? It's because here, if I'm looking at the ijth entry, this is going to be equal to 1 precisely when I is equal to j, and 0 otherwise. And this is like, you just have to look at this BTC transpose BTC. So you look at this transition, these two matrices, and if you think about it slightly, you're going to notice that this is precisely the case. And this is exactly the proof. So we have the proof for this proposition. So it's not too bad. It's nice. It's nice and fun to look at, and not too hard to show. One last remark before we end this section, and that is that if we look at the n by n matrices, so we look at all n by n transition matrices, they actually form a group, and this group is called a general linear group. For those who have seen group theory, this is a fairly well-studied group, and it's pretty cool how it functions. But basically, you just take all of the n by n transition matrices, every single one, and they form a group. And yeah, it's nice. So basically, in essence, if you're not used to forming a group, what this is basically saying is that if I take two matrices in GLN R, then Mn is also in GLN of R. In other words, if M and N are transition matrices, then M times N is also a transition matrix. And you can kind of see this just by the determinant, right? Like if we look at the determinant, if both of these are non-zero on the right-hand side, the left-hand side is definitely going to be non-zero. So it's not too hard to see. Now, the cool thing about this group, now everything we've kind of talked about is orthogonality. It turns out that if you only look at orthogonal matrices, so if we only look at orthogonal matrices, then we actually get a subgroup, which is called the orthogonal group. So this is, it's very similar to show that this is true. So it's pretty nice. So it's a nice little result that the orthogonal matrices actually give us a nice group structure. So we know a lot of information about them. So yeah, so we'll stop here for this video. In the next video, we'll talk about linear operators and basically operations we can kind of do on a vector space to get to another vector. So I will see you then. Peace.